A ball thrown upward with an initial velocity of v naught equals 30 meters per second from an initial height of h naught equals 0 meters follows an equation for its height in meters as a function of time, y of t equals negative 5t squared plus v naught t plus h naught. Determine the parts a through f. The position function, the height in meters as a function of time, is negative 5t squared plus v naught, that's a 30, times t, plus h naught, that's a 0. So we have the position function of time here. For part A, we're going to determine the velocity as a function of time. The velocity as a function of time is the derivative of the position as a function of time. The first term is power rule. Bring down the power. 2 times the coefficient. 2 times negative 5 is negative 10. T, subtract 1 from the power. The second term is a constant times t. The derivative will be the constant. So there's our velocity as a function of time. For part B, we want to determine the time when the velocity is a 0. So we can take the velocity expression and set it equal to 0. We can, solving for t, subtract 30 from both sides. And now we'll divide both sides by the negative 10. And negative 30 divided by negative 10 comes out to a positive 3. The time units can be seen over here in the initial velocity. The time units are seconds. So there's our time when the velocity is 0. For part C, we want to know the maximum height reached. And the maximum height occurs at the exact moment in time when the velocity is 0. It's stopping and turning around from having headed upward to now heading downward. And so our y max will be the height evaluated at the time when it is turning around, the time of 3 seconds, y of 3. And that will be negative 5 times 3 squared plus 30 times 3 if we plug it into the position function. And we will have negative 5 times 9 plus 30 times 3, which is a 90. And negative 5 times 9 is a negative 45 plus the 90. Works out to a positive 45. Our units here are meters, so it will reach a maximum height of 45 meters. For part D, we want to know the time when it reaches the ground again. The ground is defined as a height of 0, so we will want to know when the height is a 0, so we can take the height function of time and set it equal to 0. This has common factors of negative 5 as well as a t. If we factor in a negative 5t, the first term will have just a t left over. The second term, 30 divided by negative 5, is negative 6, and the t has been factored out. So we have 2 times t is 0, and t is also a 6. T equals 0 is the initial time when it was at the ground. That's when it was launched. T equals 6 is going to be the later time when it reaches the ground again. So we will want t equals 6 seconds. Part E, the velocity when it reaches the ground again, is going to be the velocity evaluated at that exact time when it reaches the ground, which is 6 seconds. So v of 6. Our velocity as a function of time is in part A. We can then evaluate this at 6 seconds, plugging the 6 in for the t. So negative 10 times 6 plus 30. Negative 10 times 6 is negative 60 plus that 30. Gives us a total of negative 30. And it'll have units of distance meters and time seconds meters per second. For part F, we want to know the acceleration as a function of time. And the acceleration as a function of time is the derivative of the velocity function of time, which is the second derivative of the position as a function of time. We have the velocity as a function of time in part A. We can take the derivative of that. The first term is a constant times t. the derivative is the constant. The second term is a constant with no t, the derivative is 0, so we have negative 10, and the units of acceleration will be distance, that's meters here, over time squared, second squared. So we have negative 10 meters per second squared.